Okay, before we begin, can you guys just please confirm with me in the chat that you guys can hear me, see me, and see my screen, as well as in the YouTube, that you guys can hear me clearly? Perfect. Okay, that's great. Okay, so without further ado, let's begin. Okay, assalamu alaikum and good morning. Welcome back to grade 12 physics. Okay, for those of you who might be new, okay, my name is Abdullah Ali. I'm going to be your tutor for physics, all right, grade 12. If you guys do have any questions, please feel free to ask them in the question chat, or in the chat, or in the Q&A, or in the YouTube chat if you're joining from YouTube. This PDF will be sent to the group. This PDF, along with any other notes that we do during class, will be uploaded actually to the Google Drive, and the link for the Google Drive is in the description of the group. Okay. If you did not watch last week's lesson, I would recommend that you watch last week's lesson first and then watch this lesson later on. Okay. Cool. Okay, let's continue where we left off last week. So we did this graph. We were doing momentum and impulse. Okay, we finished the first graph, which is a momentum versus time graph. Okay, now we're going to move on to the second type of graph, which is the net force versus time graph. Let's quickly just do a recap of momentum, right? Remember, we learned that momentum is the product of an object's mass and its velocity. Momentum is represented by the variable p, so it's m times v, mass times velocity. Then we discussed impulse, which we said is delta p, which is basically the change in object's momentum. So the measure of the change in object's momentum we call the impulse, okay? And anything that has delta is always final minus initial. And in this case, it's P final, which is momentum final minus momentum initial. We discussed the formulas, okay? So delta P is P final minus P initial. Delta P is also equal to M, V final minus V initial, okay? Basically, we explained how we open it up here and how we take the common factor of M because we work for one object at a time. Then we discussed that direction is extremely important for this formula. Momentum / impulse is a vector quantity. Meaning it has direction, magnitude, and direction. Okay. V final is after the collision. We deal with collisions in momentum. V initial is before the collision. We also dealt with another formula that expresses impulse as the net force of an object multiplied by the time during which that net force acts on that object. We also rearranged that formula to find another definition for the net force. Net force can be described as the rate of change in an object's momentum. We discussed conservation of linear momentum. In an isolated system, total linear momentum is conserved. So just one key thing that we might have forgot to mention, an isolated system is a system where there's no external forces exerted on it. It is basically a frictionless system. Okay. How I like to imagine isolated systems are like little boxes, okay, where it's a closed cube that you can see through, and there's just no external forces whatsoever acting on that system. Okay, no friction, no applied force, nothing like that. Okay, and then yeah, okay, cool. So then we discussed the three different cases: separate to separate, separate to united. Okay, so we're talking about before collision and after collision, and then united to separate as well. These are the different types of linear collisions that we deal with. Okay. Then we have important things. Remember, during collision, both objects have the same collision time. The force acting on each object is the same, but opposite in direction, Newton's third law. The magnitude of impulse on both objects are the same, opposite in direction. The object with less mass is always affected more, and we explain that using Newton's second law. Why are airbags necessary? We explain this using our impulse is equal to the net force times the delta T, where we said that because, what did we say? That's equal to MP final. Okay, P is constant, impulse is constant, therefore the net force is directly proportional or inversely proportional to time rather. So therefore, the implementation of airbags increases the contact time, since they're inversely proportional. When we increase the contact time, it decreases the force. Okay, and obviously the less force on somebody, the less the likelihood of injury, the less the likelihood of a serious injury, and so on. Then we discussed elastic versus inelastic collisions. We said in elastic collisions, that little sigma notation is the sum of the kinetic energy before. Why are we summing kinetic energy? It's because we have two objects. Okay, so we are summing both of their kinetic energies before, and it's going to be equal to the sum of their kinetic energies after. This is in an elastic collision. Okay, just a practical example. Energy lost. What in the world was I trying to type? Oh, I'm supposed to type out energy lost during contact. Okay, just for a practical example, an elastic collision. Firstly, it's not really realistic in a regular in the world. Okay, if collisions were elastic, if you had a bouncing ball, okay, and you dropped it from a certain height, if it had an elastic collision with the floor, it would bounce back to the exact same height forever, because no energy would be lost during contact with the floor. So that's the type of elastic collision. Okay, no energy is lost during contact. So again, if you'd throw a ball from a certain height, or just release a bouncing ball from a certain height, it would bounce on the floor and come back to that exact same height every single time. Okay, however, inelastic collisions are more realistic. It's where the kinetic energy before is not equal to the sum of the kinetic energies afterwards. So like a bouncing ball in real life, if you bounce it, it doesn't bounce to the same height each time, because every time it hits the floor, some of that energy is lost because of the contact with the ground, okay, to sound, heat, okay, it's like a contact force. Okay, so we discussed that, and then we eventually moved on to the graph, where it is a momentum versus time graph. Okay, so we just need to be careful what's given. Okay, sometimes it can be momentum, sometimes it can be velocity given. If it's velocity given, remember, then you need to incorporate that into your momentum formula, because momentum is equal to mass times velocity. Okay, so let's have a look at this object, at this graph. Okay, so we have a net force versus time graph, and we can see that initially, whatever object this is, had a net force of 0, right? It went up to 12 and then it went back to 0. So it says object A collides with object B at okay. It says object A collides with object B at 2 meters per second to the -1. Calculate the velocity of object A after the collision. Calculate the velocity of object A after the collision. Okay, so two things. The first thing to note is that we are taking right as positive, right is east. Okay, another thing to note is that this graph, okay, is for object B, object A, sorry, which has a mass of 2 kilograms, okay, and it is traveling west. Okay, so if they want us to calculate the velocity of object A after the collision, okay, so remember in momentum, the formula with velocity, with impulse, is delta P is equal to M V final minus V initial. Okay, V final minus V initial. Right? After the collision is V final. Let's just do that. After the collision is V final, so we are calculating V final. Okay, cool, perfect. Now we have the objects. On the graph, we have the objects net force during collision. 1 second. Okay, nevertheless, right, before we continue, okay, so just first thing to note is that calculate the velocity of object A after the collision. This is the formula with velocity. And since they want V final, it needs to, since they want, sorry, the velocity after the collision, we are calculating V final. Okay. Mass we were told that it's a 2 kg object. Initial velocity we know that it's traveling at 2 meters per second. Okay. And it's actually traveling west. Okay. Now, finally, so we have two knowns, one unknown so far. So we have to know what impulse is. Now that's where this graph comes in, because we need to calculate impulse utilizing the graph. Now this graph, okay, a force versus time graph, we need to note that the area under the graph gives us impulse. Area under graph equals delta P. Okay, so that is how we're going to utilize this graph to calculate our impulse by using the area under the graph. Okay, so you need to note that in this graph, net force versus time, right? We deal with area in many different graphs. Okay, net force versus time, the area under the graph gives us impulse. So in this case, the area under the graph is a triangle. So its formula is half base times perpendicular height. So its perpendicular height can be noted from here, from the apex of this triangle. That can be its perpendicular height, and we know that value is 12. Okay. We also know that the base is 0.6. So in that case, we can calculate the area under the graph is equal to half times the base times the perpendicular height. And we get an answer of 3.6 newtons per second. Why newtons per second? Firstly, we get an answer of area is 3.6. Therefore, the delta P is going to be impulse, okay, 3.6 newtons per second. To the -1. Now that we have the impulse, we can substitute it into that, okay? However, one thing we do need to note is that, okay, many times the question won't tell you which to allocate as positive, but because this question tells you to allocate the east as positive, and initially the object is traveling west, okay? Remember now, because east is positive, west is going to be negative. Because east is positive, west is going to be negative. Okay, since it's a negative direction, remember we said impulse is a vector quantity. So therefore, this guy, we are going to substitute it for the impulse 100%, but we are going to put -3.6 because it is in the negative direction. Impulse has direction. Okay, mass we said is 2 kg. V final is the question. V initial, okay, is 2 meters per second, but in which direction? In the westerly direction. So this guy is also negative because it's in the west direction, which in this question we need to consider as negative because east is positive. So you actually have to say -2. Let's divide that side by 2 or multiply out the bracket, but let's just divide -3.6 divided by 2. We get -1.8 is equal to V final plus 2. Take it over, it becomes -2, and we get a V final answer as -3.8 meters per second to the -1. So calculate the velocity of object A after the collision. Velocity includes magnitude and direction, 3.8 meters per second west. Okay, why is the impulse, not momentum, why is it west again? The impulse is west because the question tells us that object A, which is 2 kgs, is traveling west. Sorry, it's traveling in the west direction. Okay, so that's exactly why. The impulse is also going to be in the left direction, in the west direction, sorry. Okay, so I just want to re-explain it one more time. We have a net force versus time graph, and the important thing to note is that the area under the graph gives you impulse. Okay, that is important to note. So in this case, we have the initial velocity of object A. Okay, we have information that it's traveling west. We have its mass. Okay, all given in the question. They then tell us to calculate the velocity of object A after the collision. Velocity can be found in this formula here, delta P is equal to mv final minus v initial, where we have mass, we have v initial, we want v final. However, impulse is unknown, and that's why we use the graph to calculate the impulse. Once we use the graph, area under the graph to calculate the impulse, area under the graph in this specific case is not a triangle. It's not a rectangle, I mean, it is a triangle. So we use half base times perpendicular height, which is half times 0.6 times 12. We get the area as 3.6 units. And we know that the area gives us impulse, and impulse is 3.6 newtons per second to the -1. We can say west to indicate the direction, so we don't have to put the negative. However, when we substitute it, we substitute a negative because we know that's in the westerly direction. And in this specific case, we need to take west as negative, right? And we said negative 3.6 into 2, right? V final minus 2. Why is it -2? V initial, why is V initial -2? Because object A collides with object B at 2 meters per second. So we know that object A's speed is 2 meters per second, and we know that object A is traveling west. So therefore, this 2 meters per second has to be negative as well, because it's in the west direction, which we are considering as negative in this specific case. Okay, we took the 2 over to divide, then we opened this up, simplified it as plus, took it over to the other side, and we got that answer. Okay, let's move on. Let's do this question. Okay. A delivery van having a mass of 5,000 kg is moving towards the right at a constant velocity of 10 meters per second to the -1. The delivery van collides head-on with a car of mass 2,000 kg, moving at a velocity of 15 meters per second towards the left. Immediately after the collision, the car moves at a constant velocity of 5 meters per second towards the right. Okay, so that's a lot of confusing information. Luckily, it's all given in the diagram. Okay, so firstly, I'd like to say that whenever you answer a questioning, whether that be maths, whether that be physics, or for those of you that take maths, whether it be maths, you need to always read the question, the explanation. The first paragraph is the most important. You are not going to be able to answer the question without reading the first paragraph. Many of you will skip the paragraph and then go straight to the first question and try to answer from there, and then try to read back to see if you need any information. However, if you're going to read the paragraph first, you are going to give yourself an understanding of what the question is about, and it's going to help you to answer it more efficiently. All right. So yes, your objective is to always make sure that all the information in the written, okay, is in the diagram if there's a diagram. Okay. So in this case, the masses and the velocities are all there, except one thing that is not there, the final velocity. I'm just going to highlight that. Also, you can highlight. Please feel free to use a highlighter in your exam. Okay. So that I'm going to highlight so that I don't forget that that's something important I need to use. The rest of the information can be found in the diagram, which is much easier to read. Okay, let's continue. Calculate the magnitude of the velocity of the delivery van immediately after collision. Okay, so firstly, this is momentum. How will you know? You'll know by the fact that it's the same question, right? The structure doesn't change of each question, so it will follow the same order of topics of your papers. So that's one hint that, okay, this is momentum because it follows, I think it's after Newton's, they ask momentum. I don't remember exactly, but it follows the same order. So that's one way of knowing. Secondly, okay, this is a collision, okay, and you'll see things like elastic, inelastic. You'll also see things like they'll ask the definition of linear momentum. Okay, cool, right? So in this case, we just assume automatically that it is a linear collision and that conservation, linear momentum is conserved. Okay, those are two things that they do not have to mention, okay, and is assumed. Conservation of linear momentum. that there is the conservation of linear momentum and that this is a linear collision. If that is true in that case, then we can utilize our formula for linear conservation of linear momentum. Remember, our formula for conservation of linear momentum is this guy. Okay, this is actually the main formula. The separate to separate is the main formula. Okay, it is the sum of momentum before is equal to the sum of the momentum afterwards. This is a variant of that formula. It's the same thing essentially. And this is also a variant of that formula and is the same thing essentially. But this is the main formula that can be used for anything. Okay, these are just simplified versions to make it easier for some people or to take a shortcut. Okay, but this is the main formula for conservation of linear momentum. So whenever we're dealing with this type of collision, we are going to use this conservation of linear momentum formula. Okay, so it says, number one, calculate the magnitude of velocity of the vehicle of the delivery van immediately after collision. So conservation of linear momentum, 3.1. So we have two things. We have a car and a van, this car and this delivery van. So that's why we add up the momentums initially. So M times V, I'm going to call it M1, the mass of the first object, V initial, plus M2 V initial is equal to M1 V final plus M2 V final. Okay, so let's object one, let's consider it the van. So its mass is 5,000 kg and its velocity is 10 meters per second to the -1 to the right. Okay, so in order for us to put down the velocities again, because we're dealing with conservation of linear momentum, which is a vector quantity, linear momentum, vector quantity. Remember, linear momentum is a vector quantity with the same direction as the velocity of the object. That's important. The direction aspect is important because we need to choose a direction as positive. So here I'm going to choose the right as positive. Therefore, everything to the left is going to be negative. Everything to the right is going to be positive. So the van is initially traveling to the right. So its mass is 5,000 kilograms. And its initial velocity is positive 10. Why? Because it's traveling to the right. And I said that right is positive. Let's talk about the car initially. It has a mass of 2,000 kilograms, but it actually has a negative velocity. Why? Because it's traveling to the left. So 2,000 times -15, 2,000 kilograms. Our unit is kilograms, by the way, times -15. So these are initial amounts for both objects. Let's do the final amounts for both objects. So the mass doesn't change of the objects, right? Sometimes it does if the two objects combine, but in this case, it doesn't change. So it's still 5,000, which is basically 5 tons, 5,000 kilograms. Okay, so they tell us here, immediately after the collision, the car moves at a constant velocity of 5 meters to the right. So the only final velocity, meaning after collision, that we have is for the car. They actually want us to calculate the velocity of the delivery van immediately after collision, or the final velocity of the delivery van. So we need to know this velocity. So this V final is unknown. However, for the 2,000 kilogram car, we do know the final velocity. It is 5 meters per second towards the right. So since it's towards the right, it is a positive velocity of 5. Okay, direction is extremely important. Okay, cool. So now all that's left to do is to simplify. How do we simplify? I'm just going to put all of this in my calculator and get one final answer. So 5,000 times 10 plus 20,000, sorry, 2,000 times -15. I get an answer of 20,000. Let's hope that's correct. Someone just check along with me. Is equal to 5,000 VF plus 10,000. Yeah, that is correct. So we take it over as a subtraction. It becomes 10,000 is equal to 5,000 VF. Divide both sides by 5,000 or take 5,000 over as division. Same thing. You get the V final as 2 meters per second. Since we are dealing with vector quantities, we should also get a negative or positive in our answer. In our answer, we actually got a positive, which means it's in the positive direction, which means it's to the right. That's how we know the direction. Because in our calculation, we considered negative and positive. Okay, so therefore our final answer is going to give us an answer as a negative or positive. And whether we get negative or positive, that would indicate to us the direction. Okay. Let's move on to the next one. Calculate the change in kinetic energy of the system. Okay, so change in kinetic energy of the system, that is delta K. Change in kinetic, which is EK final, which is kinetic energy final, minus EK initial. Okay, so remember of the system, keyword system. You're not just talking about one object. They want of the system, meaning both objects. Okay, so 3.2, let's do the calculation. I'm going to calculate delta EK, which is equal to EK final minus EK initial. So let's calculate EK final. EK final is basically the kinetic energy of both objects after the collision. So after the collision, what is the formula for EK? Formula for EK is half mv squared. So we can calculate the EK because we know the velocity as well as the mass, of course. So I'm going to do it for the 5,000 ton, 5,000 kilogram van. Remember the 5,000 kilogram van final velocity, its final velocity is 2 meters per second. One thing you need to note is that for elastic and inelastic collisions, energy is not a vector quantity, it's a scalar quantity. So we don't consider negative. Always for energy, okay, substitute positives. So it doesn't really matter for kinetic energy about the negative. You're just substituting values. You always just substitute a positive value. So that's why in this case, I don't care whether it's negative or positive 2. I'm just going to substitute 2. And now I need to add, because remember, this is the EK final of the system. So for both objects, I'm going to do for the second object, it's half times 2,000 kilograms, the weight of the car. And remember, its final velocity, they said, was 5. When we do this calculation, I am forgetting one thing, is that it's squared. So I need to square the velocity, okay, just the velocity, not more than that. When I do this calculation for EK final, I get an answer of 35,000. The unit here is joules, energy, joules. Let's do EK initial. EK initial is going to be half times 5,000. Okay, initially the vehicle was traveling at 10 meters per second. It was traveling to the right, but it doesn't matter whether it was right or left, negatives and positives. We don't substitute negatives and positives into our energy formulas. Half times, what is the mass of the car? 2,000. And initially, this guy was traveling at 15 meters per second. It was negative, but I don't have to substitute negative into my energy formula. Remember, it won't even matter because you're squaring it. You'll get, even if you put a negative there, you'll get positive. Yes, correct. If you get a decimal for your final velocity, you would round it off to 2 decimal places, and you are most definitely allowed to use it in the next question. 100%. Okay, when I do this calculation, I get 4. Is that correct? 475,000 joules. Okay, so delta EK, right, is delta EK is equal to EK final minus EK initial, right, which is 475,000 minus 35,000. When I do the calculation, I get negative 440,000 joules. This is the change in kinetic energy. It's not such a common question, but you have to just understand the logic of it. Change. You have to know how to do kinetic energy. You have to understand what is change and then do the calculation. Number 3.3. What type of collision this is? Is this, sorry, right only elastic or inelastic? Please, you guys tell me. What do we think? Is this elastic or is this an inelastic or is this an elastic collision? Elastic or inelastic? Inelastic, 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 inelastic. Okay, why? Why is it an inelastic collision? Why are we saying that it's an inelastic collision? Okay. I see there's many correct answers. Correct. Most of you are indeed correct. It's because the kinetic energy is not conserved. The sum of the kinetic energy before is not equal to the sum of the kinetic energy afterwards. One person said velocity decreases. So that is true. Velocity does decrease, but a decrease in velocity does not necessarily mean that there'll be an overall inelastic collision. Okay. Okay, why is the answer negative? Okay, the answer is negative because we took sorry. Good point. This is supposed to be the other way around. And therefore it is supposed to be negative. I just wrote this the wrong way around. This was the initial and then that was the final. So that's why we get negative. Thank you for that. Okay, but basically the EK final is not equal to the EK initial, right? So we can see that because we already did the calculation, right? Now, sometimes they could ask this question and it would be for 4 marks. Okay, you would have to do the calculation yourself, right? 3 or 4 marks. In this case, it's inelastic, and they say write only that. Okay, they say if the collision lasts for 0.4 seconds, calculate the magnitude of the force that the delivery van exerts on the car. If the collision lasts for 0.4 seconds, calculate the magnitude of force that the delivery van exerts on the car. Let's just write the reason here. Sum of EK before is not equal to the sum of EK after. If the collision lasts 0.4 seconds, calculate the magnitude of the force that the delivery van exerts on the car. Delivery van exerts on the car. On the car is the key word, people. If it's delivery van on the car, we are going to be using values for on the car. Now, you could use values for the delivery van, but remember that it's going to be opposite signs, okay? Because again, force vector, so it needs direction. So if you're going to be using values for the delivery van, okay, you're going to be getting values of opposite signs. Okay, so let's do the calculation. Net force, remember, we have 2 formulas. Delta P is equal to M, V final minus V initial. And delta P is equal to M, no, not M, sorry, F net times delta T. In this case, they want delta T, okay? They want net force. We were given delta T, okay? We have the mass, of course. We actually have the final and we have the initial. So this is actually where we now combine the 2 formulas and we say that F net times delta T is equal to M V final minus V initial, because we didn't calculate impulse yet, but we do have M V final and V initial. These two formulas can be combined because they're both equal to delta P. So now in this case, remember on the car, the net force exerted on the car. So we are going to use the values for the car. So F net times delta t. F net is the unknown. Delta t, I believe, was given as 0.4. Okay. The mass of the car is 2,000 kilograms. Its final velocity, okay, this is impulse, so we need to consider direction, okay, because direction is important. It's a vector quantity. So final velocity is 5 meters per second to the right. So it is actually a positive velocity. However, its initial velocity is 15 meters per second to the left. It's actually a negative velocity. So minus 15. Okay, you can put this entire thing in your calculator. 2,000, open brackets, 5 minus 15, which is basically 5 plus 15. You get 40,000. Okay, when you do this calculation, and you're going to divide it by 0.4, divide both sides by 0.4, and it cancels. When you divide it by 0.4, you get the net force as 100,000 newtons. Okay, is someone doing it along with me? Can you confirm that this is the correct calculation? Okay, since we got a positive answer, that means it's to the right direction. And that makes sense because, see, it says calculate the magnitude of the force that the delivery van exerts on the car. Delivery van on the car, delivery van on the car. The delivery van, okay, is traveling to the right and it knocks the car to the right. Okay, before I answer this person's question, tell me, so we've got the net force that we've got the net force that the van exerts on the car. Van exerts on car. Okay. Somebody tell me what would the net force be that the car exerts on the van? We have net force of van on car. I want to know car on van. Net force. Remember, net force is a vector quantity. Same but opposite direction. Yes. Same. It will be the same. For those of you that are saying the same, it is technically incorrect. It is negative 100,000 newtons. That is the correct answer. Or same but opposite direction. Newton's third law isn't the force of the same but opposite. Yes, correct. Okay, so you have to specify direction. Okay, so it's not exactly the same, okay, because technically we are dealing with a vector quantity. So 100,000 and negative 100,000, remember we said in physics, they are not different in magnitude, but they are different in direction. And 100,000 is technically not less than negative 100,000. They're just opposite in direction. Yes, correct, Brown. They are the same, but different direction. Okay, perfectly. Okay, so now I just want to answer this question. Somebody asked, why are we so focused on calculating the net force on the car instead of on the van? Okay, so firstly, because let's read the question and what they specifically state. The question states, if the collision lasts 0.4 seconds, calculate the magnitude of the force that the delivery van exerts on the car. They tell us, okay, they tell us that they want to know the force that is exerted by the van onto the car. Since it's on the car, we need to use the values that the car experiences. So the final velocity of the car, those values of the car is going to tell us the net force that the car experiences. If we are going to use values of the delivery van, it's going to tell us the net force that the delivery van experiences. Okay? Even though it's by the van onto the car, we just focused on the car because they want to know on the car. So no matter what type of force around it is exerted on it, we need to focus on the values of the car and it will give us those forces exerted onto it. Okay, I hope that makes sense. Okay, instead of the starting vertical projectile motion, I rather we continue with another question. Okay, let's not rush through the syllabus. I know many of you are busy with vertical projectile motion, but I hope that we have enough weeks to complete vertical projectile motion in time and then eventually get to organic. Okay, so the diagram below shows two skateboards, A and B, initially at rest, okay, with a cat standing on skateboard A. We didn't skip a question, right? Okay. With a cat, where are we? For the cat standing on skateboard A, the skateboards are in a straight line, one in front of the other and a short distance apart. The surface is flat, frictionless, and horizontal. Again, they don't have to mention these specifications, but these specifications make it more obvious. Which ones? Firstly, we have straight line, and we have flat, frictionless, horizontal. Flat, frictionless, horizontal. So horizontal, straight line, those indicate, and flat indicate linear, okay? Frictionless indicates an isolated system, which indicates isolated system, linear momentum, and conservation of linear momentum. On 3.4, I got 275 joules, not 475. You might be correct. Let's double check. Did you square? You might have forgotten to square your values. But I'm going to quickly double check. No, you are correct. No, wait, you're not correct. Did you use 5 instead of 15? Because now I used 5 instead of 15 and I got the value that you got. I think you might have used 5 instead of 15, just the exact mistake I just made. But when you use 15, you get 475,000. Okay, so just double check your value. Okay, so yes, again, these specifications do not need to be mentioned for us to assume ourselves that it is conservation of linear momentum, but they are mentioned in this case, which just confirms to us, okay, conservation of linear momentum. Why? Definitely linear. Frictionless means it is isolated system, which means that since it's an isolated system, there will definitely be a conservation of linear momentum. Cool. Firstly, state the principle of conservation of linear momentum in words. The principle states that in an isolated system, linear momentum is conserved. Generally, not generally, many times, okay, which are similar things, but many times when they ask the definition of a principle or any definition, yeah, I used 5 too somehow, and I got your answer. Okay, so when they ask a definition or principle, many times in the next question, they are going to test you on that principle, okay? And it's not definite that you are going to use the formula that comes from the principle, but you will definitely be able to use the formula that comes from that principle. Most of the time. It's not 100% of the time, but why I tell you this is because just say you're stuck many times, especially when we do like work energy power, people get confused which formula to use when. So this is a hint. If they ask you the definition, generally in the next question, you don't have to use the formula that comes from that definition, but it is definitely an option to use that formula that comes from that previous definition. Okay, cool. So meaning in the next question, we most likely will be able to use conservation of linear momentum. So they say that, let's just steal all the information we need from this first paragraph so we don't have to scroll back up. They are initially at rest, okay, with a cat standing on skateboard A. Let's do this. Okay, cool. So we just need to know that they initially at rest. That's the most important thing from there. Right. Each skateboard has a mass of 3.5 kilograms. The cat has a mass of 2.6 kilograms, and it jumps from skateboard A with a horizontal velocity of 3 meters per second and lands on skateboard B with the same velocity of 3 meters per second. Okay. Refer to the diagram below. Okay, we have a cat jumping from one skateboard to another. Calculate the velocity of skateboard A just after the cat has jumped from it, immediately after the cat has landed. Okay, so by the way, this immediately after the cat has landed, that's for the next question. Okay, so that's to do with 4.3. Question is asking, calculate the velocity of skateboard A just after the cat has jumped from it. Okay, so we have one of those cases where, okay, actually you guys tell me. So calculate the velocity of skateboard A just after the cat has jumped from it. Okay, so we are working with skateboard A and cat. Which case are we in? In that specific scenario, which case are we in? Are we in case 1, separate to separate? Are we in case 2, separate to united? Are we in case 3, united to separate? Which case are we in? Just dealing with the skateboard and the cat. Okay, very good, correct. Yes, we are in case 3 indeed. Okay, because united to separate, because initially the cat and the skateboard are one. Basically, they have one mass, and then the cat decides that he wants to jump off, and therefore they are now separate. Okay, so we're dealing with it one skateboard at a time. So yes, we're in case 3, so you can utilize this formula. I will reiterate that you can use case 1's formula for anything in conservation of linear momentum. They are essentially the same thing. It's just that, yeah, I took the common bracket of the initial velocity, because the initial velocities are the same because they are one object. So, yes, immediately after the cat is landed, the cat and the skateboard move horizontally. Okay, sorry, we still budget 4.2. So calculate the velocity of skateboard A just after the cat has jumped. So I'm going to, because I know that I'm in case 3, I'm going to write case 3's formula, which is V initial, because they have one initial velocity, and I need to combine their masses. Mass of A, which is the skateboard, mass of B, which is the cat, is equal to, since they separate after, I will have MA or M1, it doesn't really matter, V final plus MBV final. Okay, the mass of the second object with its final velocity, since they are separate. Now, initial velocity, do we have? Yes, we do. Okay, remember they are both stagnant. We have the masses of both of them. Okay, the final velocity of A, which we call the skateboard, that's what they want us to calculate. So our unknown is this. So you see, this is a good way to approach the question. Always note what is wanted from you. What is the unknown and what do you know? Right? So they want the final velocity of the skateboard. The final velocity of the cat, we do know indeed. Okay, so let's do the calculation. V initially is 0. It doesn't matter what this is. It makes the entire thing 0. 3.5 plus 2.6. It really doesn't matter because that entire thing is going to be 0. Mass of A, 3,5. Right. The velocity. Okay. So let's choose the direction as positive. I'm going to choose right as positive. Why not? Okay. So the final velocity of the skateboard, that's what we need to calculate. So we can just leave that as V final. Now, 2,6 is the mass of the cat. The final velocity of the cat is to the right. Okay, it shows us in the diagram. It's a positive velocity, which is 3 meters per second. Now we have 0 is equal to 3,5 times V final. 2,6 times 3, that gives us 7.8. Take it over to the other side, it becomes negative 7,8 because I take it over. So positive is equal to 3,5 V final. Divide both sides by 3,5 or take 3,5 over as a division. Both are the same thing. You get a V final of negative 2,23 meters per second to the negative 1. Meter per second to the negative 1. Not our final answer. It's a vector quantity. So we want to actually leave our final answer not with a negative, but with actual direction. We will say, because it's a negative, we will say to the left. Okay, so please do note that, yes, it makes sense, right? If a cat is standing, why is the initial velocity 0 and not 3? Yes, they mentioned that it was at rest. They were stationary, very good. It's in the first line, the two skateboards A and B are initially at rest. Okay, then after they are at rest, the cat decides to jump with that velocity so that its final velocity once it was separated. Okay, and it makes sense. If this cat is going to jump off the skateboard, obviously it's going to exert a force onto the skateboard in the left direction, then it's going to move to the left. Okay, let's look at 4.3 quickly and let's try and answer it before time ends. Well, it's already over, but we'll end slightly late. Calculate the magnitude of impulse on skateboard B. Okay, again, keyword on skateboard B. We're going to use skateboard B's values, okay, as a result of the cat's landing. Okay. Okay. Calculate the magnitude of impulse on skateboard B as a result of the cat's landing. So let us consider the initial velocity of this guy is 0. Okay, so firstly, impulse is delta P is equal to mv final minus v initial. There's also the one with force, but I don't think we're going to use that one because there's nothing mentioned about force, nor is there anything mentioned about contact time, and they don't want net force or contact time or mass or velocity. They want impulse. So we need to use one of these, and we're most likely going to use the first one just because in net force is not mentioned. Now, again, it is force, so we're going to say delta P is equal to, we already wrote the formula on top, so I'm not going to write it again. We are dealing with skateboard B, so it's on skateboard B. On skateboard B. So firstly, its mass is the same as the mass of the other one, 3,5. Its final velocity. Can someone tell me what is its final velocity? Oh, okay, we have to read the question. It says that immediately after the cat has landed, the cat and skateboard B move horizontally to the right at 1.2 meters per second to the -1. So we know its velocity. Now remember, the cat lands with 3 meters per second, but it actually makes sense that when it lands, okay, some of that force that it lands with is lost due to the contact with the skateboard, and therefore it doesn't move at 3 meters per second. It's also due to the weight, perhaps, of the skateboard that they don't actually move at 3 meters per second. They move at 1.28 to the right, which is our positive direction. So it will be a positive 1.28 minus its initial velocity is, of course, 0. Why? Because it was at rest. So therefore, we get the impulse of the skateboard B as 3.5 times 1.28, basically, and it is 4,48. Okay, I just want to double check. This is newtons per second, or actually, mass times velocity, kg meters per second to the -1, because we used m times v. Okay, I just want to double check. Remember, we said that impulse of both objects are the same but opposite in direction. In 4.2, why is the initial velocity 0? Because they are at rest. Remember, both skateboards are at rest. Okay, I just want to double check that we get the same impulse when we work with this guy, L cat. Okay, this is equal to its mass, which we said was 2,6. Its initial velocity, its final velocity, sorry, is what the skateboard 1,28. Its initial velocity is 3. Remember, it landed with 3. Okay, and jumped at the horizontal velocity of 3. And we get 2.6 times 1.28 minus 3. Indeed, we get -4,47 and 48. So very close, obviously not exact, but that's just because life. Okay, but it doesn't have to be exact. They are very similar, but I'm just showing you that the cat and the skateboard during their collision have the same impulse, just one is negative, right? When we use the information of the skateboard, we're going to get its correct direction, which is positive, and then its correct direction, which is like a negative impulse. Why don't we use 3 for the V initial, as that's what the cat jumped with? Okay, that's a good question. Why don't we use 3 as the initial? Okay, why don't we use 3 as the initial, as that's what the cat jumped with? That is very specifically because we are dealing with on skateboard B. We want to know the impulse on skateboard B. So this information, all of this information is the skateboard's information. And this, that's why I did this one. This is when we use the cat. So you can see we get the same answer, just opposite direction. But here I use the cat's mass, the cat's final velocity, the cat's initial velocity, and I get the same impulse as when I use the same magnitude of impulse, or when I use the skateboard's mass, its final velocity, its initial velocity. Why is the unit of impulse meters per second to the -1? It's firstly, it's kg meters per second to the -1. It's not 100% important, but basically it's equal to mass times velocities, if you'd like, v final minus v initial, right? Mass is kg, this is meters per second to the -1. So therefore, it's kg meters per second to the -1. Okay, it's not as important, but yeah. I mean, for the cat. Again, because I used masses and velocities. Oh, sorry. I see what you're saying. Sorry. Sorry. Is it the same as newtons per second to the -1? Yes, it's exactly the same. Newtons per second to the -1 comes from F net times delta t, which is also impulse. So you could use either one, right? I would just recommend using for mass and velocities, use kg meters. And whenever you use F net times delta t, you need to use newtons per second to the -1. Okay. Okay, cool. Right, so that's those questions done. Okay, people, please practice more examples, go through different cases. Okay, and you should be ready for momentum. Momentum is not too bad, right? You just have to have an understanding of linear momentum, which case you're in. When do we tackle VPM? Next week, we will start, indeed. We are done with momentum. Next week, we will start vertical projectile motion. Okay, and then move on again to organic. But yeah, thank you guys so much for joining. It was a pleasure to teach you guys. Yeah, please note that I'll send the notes to you guys. So be on the lookout for that. And I'm not sure what you mean. How far have you come with our classes? We've only done momentum so far, if that's what you're asking. We've done over the 2 weeks, we've covered momentum. Okay, cool. So I have to end so that I can start the next class.